Okay, this is part 3 of trying to read Milne. It's Appendix 7, the apparent brightness of a receding nebula, and this I am saying is a prediction of the cosmic microwave background radiation from 1935. This is part 3, and I'm continuing where I left off. We had an emitter, which is a surface of a nebula. We had a receiver, which is basically the aperture of a telescope. D omega prime is where I was at, and d omega prime is the surface, is the angular surface area, which comes from, which is the surface through which the light from an event at point B at time 0 in the perspective of the nebula. So this is a single event, and maybe it's I don't know the details of the event, but we're assuming that it's kind of a point in space and time, and that point in space and time produces a light in a direction, and this is a surface area in steradians. It's a solid angle. And this ds prime is the telescope's aperture area in the nebula's point of view. This I prime is the direction from event B to event A in the nebula's point of view. And this n prime, I'm going to call it the direction of photon sweep. The direction of the photon sweep of photons from event B. So it's not exactly the same as the direction the telescope is aimed, but it is the direction that the telescope captures, the direction that the telescope needs to be pointed in order to capture every photon coming in that direction from point B. So let's call that the direction perpendicular to photon sweep. So it's not quite the same as the direction that the telescope is pointed, but it's basically the same as the direction that the telescope is pointed. So, from the perspective of this guy here, the nebula, the region through which light from this event the region through which that light can go through that will strike the surface of the telescope is d omega prime. And d omega prime is equal to the dot product of I prime and n prime times the surface, that ds prime, the surface of the photon sweep, divided by r prime squared, and r prime squared is this distance here. So r prime squared would essentially be a surface area that extends all the way around that event at that distance. Well, actually, the whole surface area would be 4 pi r prime squared of the entire region over which, if this event sends out emissions in all directions, the area would be 4 pi r prime squared. But that surface area would be a measure of 4 pi steradians. So 4 pi steradians would be the entire sphere, and d omega prime here is somewhere less than 4 pi steradians. So if ds prime extended as a complete sphere around point B, then ds prime would be 4 pi r squared, 4 pi r prime squared. 4 pi r prime squared over r prime squared would just give you 4 pi. And then your solid angle for that entire sphere would be 4 pi. So this is going to be way, way, way less than that, because if this is a nebula and this is a telescope 4 billion light years away, then this is going to be a very, very tiny number. Of course it's not. We're going to see this 4 billion light years away, but in fact, from the perspective of that nebula, no, it is going to be a long distance, isn't it? As a matter of fact, it's going to be a huge, it's not going to be 4 billion light years, it's going to be like a billion light years from this event to this event from that guy's perspective. Probably not that much. Probably just 1100 times 40 billion light years. So about 400 trillion years, I think, if I did that right in my head. Anyway, this is going to be a teeny tiny number because r prime squared is going to be enormous when r prime is 400 trillion years, or light years. So now we want to consider the energy that would be received by the telescope from the section of the nebula surface in the interval from t prime to t prime plus dt prime of the nebula's experience. Now this is a long time after it's emitted. That's going to be a long, that t prime is going to be long after the emission. If ds prime were stationary at A, that is, if the telescope were stationary at A, at point A, the amount of energy it would receive a long time after the emission, and just a little bit after that, would be, by the general theory of radiation, this is the intensity. The intensity is given in, or the frequency-dependent intensity would be in joules per second. That's the amount of energy per second, or watts, divided by per hertz, because this is going to be joule per second between, for instance, 290 hertz and 291 hertz, or between, say, 5 billion gigahertz and 5 billion and 1 gigahertz. But it's also distributed over the surface area of the nebula, so that is per meter squared of nebula, and it is also per steradian of the aperture. And that's a steradian of the aperture measured from the point at the center of the nebula surface. So we're going to multiply that by d nu. Did I say what d nu is? D nu is the spread of relevant frequencies over which the intensity can be said to be relatively constant. and that is emitted, and they've got to be, those frequencies have to be emitted by the nebula and detected by the telescope. So that's a specific set of frequencies. Then ds naught prime is going to be measured in square meters because it is the surface area. Let's say it is the surface area of the nebula that is detected as a pixel by the telescope. And by pixel, I mean the smallest distinguishable feature by the telescope. So surface area of the nebula of that appears as the smallest distinguishable feature of the telescope. So I got that. Now I prime dot n sub naught prime is the cosine of the angle the nebula surface is pointed away from the telescope. So if somehow part of the nebula is blocking this, so the surface may be pointed like away from the telescope, and you would end up with 0. But as long as this is between 0 and 90 degrees, or negative 90 and 90 degrees, then the nebula surface is pointed towards where the telescope receives receiving, let's call it the perception event. So if that perception event, if the nebula surface is pointed directly towards that perception event, then this is going to be 1. All right, now the d omega prime. The d omega prime is the Steradian solid angle measure of the locus of events where the emission is detected from the event at the center of the nebula surface at time t prime equals 0 by the telescope aperture. So that is what d omega prime is. Sorry, nothing here is simple. And by the way, that's the only difference between these two equations, or the left-hand side and the right-hand side, that d omega prime is ds prime times I dot n prime over r prime squared. But before I get to that, let's go to dt prime. dt prime is the amount of time over which the watts of power are received by the telescope in the nebula's point of view. And I think actually I already covered why d omega prime was equal to ds prime times I prime dot n prime over r prime squared up here. So we'll just move on now. Okay, when ds prime, that is the telescope, when the telescope aperture is in motion, the amount of energy it receives is altered. It says let m denote the position of ds prime of the telescope aperture at t prime, and n represent the position of the telescope aperture at just a little bit later, t prime plus dt prime. Project ds prime at A conically from B to the plane of n, and call this projected position, conically to n. So project ds prime at A, ds prime at A, this whole surface area, and we're going to project it conically from B, so from this point, from that event onto the plane of n. So this plane, and this is, is this a plane? It's a plane in space-time. Okay, so M is a locus of events which are not quite simultaneous in the nebula's point of view. And also N is a locus of events which are not quite simultaneous in the nebula point of view. But we can be sure that this event A happens at t prime, and A prime happens at t prime plus dt prime. So this event, I guess, does this event go to t prime plus dt prime as the projection of A to P, and then the other events go parallel to this in space-time? Or I'm a little confused by that, but so project ds prime at A conically from B. So we create a cone that extends with point B onto the plane of N and call this projected position P. Then the telescope aperture would be just slightly smaller. This solid angle here would be slightly smaller at t prime plus dt prime than it was at t prime. However, what if the velocity is not directly away, but some other direction? Then we could say that this is also slightly smaller. However, it's not as much smaller as it would be if it was moving directly away. Then the radiation crossing ds prime, the surface of the aperture of the telescope, as the aperture crosses from m to n to the first power of the differentials concerned, is equal to the amount of the radiation which would have crossed ds prime had it passed from m to p to the first power of the differentials concerned. Now it won't pass from s to p, but he's saying that the amount of radiation passing that the object would have been exposed to if it had grown, if the telescope aperture had grown so that the d omega prime remained constant, and it moved directly away, is approximately the same as the actual amount of radiation captured from events during that time, coming in on its actual path. So let's put it this way: E actual, which is the energy absorbed, the energy that passes through the aperture going from here to here, equals E pretend, which is the energy that goes through the aperture if you imagine it going from here, expanding as it goes away, directly away from the surface, minus some first power as it passes from m to n, the first power of the differentials concerned. So k times differential of E to the first power. The error is in fact of the order of the energy passing through the curved surface of the cylinder formed by the motion ds prime from m to n. The error is of the order Right, something makes me want to do something like this and extend that up to there and create another cylinder up at the top of this thing so that we can imagine the area of, or the amount of radiation that passes through that whole cylinder. And this energy is equal to the difference between the energies that would cross in the same time the area ds prime stationary in the positions m and n respectively. So he's imagining E at m stationary versus E at n stationary. And we're saying that for some reason that E actual minus E pretend, that's right, E pretend minus E actual is greater than E sub m minus E sub n. Okay, let me make another case. If the velocity is straight out, if the velocity of this thing is straight out from here to here, then E sub p minus E sub a would be equal to E sub m minus E sub n, because the energy that would come through, well, you'd really be looking for the difference between the volume of a cone and the volume of a cylinder, because this is cone-shaped, so the radiation going into that cone, so you would be including all of the radiation going into that cone, versus the cylinder shape, and you'd be involving all of the radiation going into that cylinder. Anyway, what I do know is when this is going to be a point that is several billion light years from this, then we can probably just say ignore that cylinder, because this angle is between the vertical lines of the cone and the angular line of the cylinder is going to be so tiny that you can just neglect it. So, especially in the argument where we're actually having the thing travel directly away from the object, from the nebula. So whether this argument is actually valid or not for a situation where the velocity is perpendicular to the direction, I feel very comfortable in saying that the argument that the amount of light coming through this cone is going to be insignificant, that error would be insignificant compared to this thing here. And I think that's what his next point is. The amount of energy falling on ds prime, let me copy that image down, in its motion from m to p is less than the amount that would fall on ds prime if stationary. Okay, this is what they're saying. Let's call that the actual motion from m to p. Let's start over. Now the amount of energy falling on ds prime in its motion from m to p is less than the amount that will fall on ds prime if stationary at point m by the amount of energy trapped. It's not really trapped, but okay. Trapped in the truncated cone cut off between m and p as subtended from b. But ds prime does not move from m to p. it moves from M to N, and is not less than the amount, it's not the amount of energy trapped in the truncated cone, it's the amount of energy trapped in the outside of this cone, not including the cylinder. But otherwise, I think he's on the right track. It occurs to me that this might be a typo because ds prime doesn't really move from M to P. That was just an imagining. Well, I think I'm going to leave it there for now. Thanks for watching, and farewell.